Okay, so we've seen our double slit equation, and it's simply d sine theta is m times lambda, and we've already fully explained all the variables. So I've got a diagram here that labels d and theta, and even shows lambda on the left, and it shows the location of our antinodes, and we see a little pattern here. And what we want to do now is see what the relationship is with the actual shape of the pattern and these variables themselves. Now before we start, a little bit of math review. Here's a typical sine curve, and if you recall, sine starts at 0 and then rises up, so it reaches a maximum at 90 degrees and then back to 0 at 180, and the whole pattern repeats itself again at 360 degrees. Now on our diagram we can see that theta is never going to go past 90. It's going to be between 0 and 90. And on my sine diagram we see that between 0 and 90 sine theta continues to increase. So for this purpose, as theta goes up, sine theta goes up. So now let's look at the relationship between sine theta and lambda and d. So let's rewrite our equation for sine theta because that represents our pattern. So we see two relationships here. We see a direct relationship between sine theta and lambda, which means that as lambda increases, sine theta will also increase. So the pattern should stretch apart, because on our picture we see that if theta suddenly gets larger, that means the location of m equals 1 will be further up. So our pattern will stretch out. We also see an inverse relationship between d, the separation of the slits, and sine theta. So if d gets larger, so if the slit separation gets larger, then sine theta actually gets smaller and our pattern should squeeze. Let's see this effect with a simulation. Okay, so in this simulation we can control the spacing between the slits with this slider. We control the width of the slits themselves with the bottom slider. And if I click on the light, it'll change from red to blue. Let's first look at the effects between wavelength and the pattern shown on the screen. And if you'll recall, we said that sine theta was directly related to lambda. So if lambda increases, sine theta should also increase. Now, what if lambda decreases? Well, a direct relationship would mean sine theta would also decrease. So let's have a look at our first pattern, which is the red light. And when I click on the light, it's going to change to blue. Now, blue has a shorter wavelength than red. So lambda will decrease, so the pattern should decrease, and it should squeeze together. Sine theta should get smaller. And we see, in fact, that that is the case. So we've proven the first point. As lambda gets smaller, sine theta gets smaller, and as lambda gets bigger, sine theta gets bigger, and the pattern stretches apart. Now what about the slit spacing? Now if I increase the spacing of the slit according to our equation, we should get a decrease in sine theta because we have an inverse relationship. So if the slit spacing gets larger, we see that the pattern squeezes together because sine theta gets smaller. And if the slit spacing gets smaller, the pattern moves apart. Sine theta gets larger. Now down below we see our slit width, which we're not really worried about. But basically it just tells us how intense the actual pattern is on the screen. As the slit width gets wider, the intensity gets smaller. But again, we're not really worried about that one. We're only worried about the slit spacing and the wavelength.